I have the pleasure of introducing Dr. Alexis Ault from Utah State. I have enough indirect connections to Alexis over the years that I feel like I ought to know her way better than I do. So she was an undergrad at Wellesley College, which has a close link to MIT. So she did MIT's field camp, and one of my office mates from graduate school was one of her professors in that. She went on then to a master's at University of New Mexico with an old friend and research collaborator of mine, James Silverstone, and on for a PhD in Colorado with Becky Flowers, who many of you know as a master's student here and a running partner of mine.
Soon to be a running partner of mine, apparently.
Apparently.
Gonna pace her.
With Becky, he started working on low temperature thermochronology, which he then pursued as an NSF-funded postdoc at the U of A with Pete Reiners. And that work, she actually gave a talk in this, at a distinguished lecture here several years ago, where she was working at length scales of hundreds to thousands of kilometers and time scales of hundreds of millions of years. And when she moved to Arizona, both of those scales changed drastically.
Yes.
To work on something that I regard as one of those things that's sort of been on my wish list for my whole career, and probably for many careers before mine, being able to determine the age of fault movement from the rocks along the fault. Okay. And so the progress that she's made on that, it's led to an NSF Career Award, being named the Outstanding Researcher of 2018 at Utah State, and being awarded the Naser Prize by the Geochronology, Thermochronology section at GSA in 2018. So it's pretty exciting stuff, and I hope you're as excited as I am to hear about it.
Yeah, oh, awesome. Okay, well, thank you so much, John, for that introduction. We are like second cousins, twice removed, or something like that. Yes, actually, I was reflecting on the fact that when I was last here giving a talk, at the very end of the talk, I showed some of the very first hematite uranium, thorium, helium thermochronometry data that I had acquired as I was just starting my NSF postdoc at the University of Arizona. And I made some really arm-wavy interpretations and promptly went back to the lab and got some more data, and all of a sudden the data set was not scattered by 7 million years, but 100 million years. And I had a lot of work to do. The hematite uranium, thorium, helium system is quite complicated, and I'm excited to share with you all some of the advances we've made in our ability to interpret dates using that thermochronometric tool, and specifically focused on what are farts in geologic time, right? So it's to shorten our timescales, but specifically thinking about processes that are instantaneous and what their record might be in rocks. And so we're going to look at exhumed fault zones. Of course, before I get started, I would be remiss if I didn't thank a number of graduate students and postdocs and colleagues from a number of institutions who have made this work possible. It is indeed a collaborative effort, and I'm excited in particular to highlight the work of members of my research team. It's their tenacity that has made this work possible. In particular, Rob McDermott is a PhD student in my research group, Amy Moser, a former master's student, Gabriele Calzolari, a former postdoc, and several undergraduate students. Oh, Leah Hauser, a master's student, will show some of her work today. And I have a number of collaborators. You may recognize some of these names. Jim Evans at Utah State, Pete Reiners, my former postdoc mentor, Jonathan Kane at the USGS, Greg Hirth at Brown Deformation Experiments. I'm going to show some of those results today, and Brian Vandevenner, who has been instrumental in helping us look at rocks at the nanoscale. So some of you, perhaps if you've been in one of Pete's classes, have seen this diagram. Oh dear, now there we go, Pete. This is what you told me was going to happen. But seen this diagram from Christy Rowe and Ashley Griffith. This is one of the figures from her JSG review paper. Okay? And what she and Ashley are plotting here is rupture velocity as a function of slip rate, and they're showing you here a number of observation points of how rocks deform from seismic slip, so earthquakes, to slow slip events, episodic slip and tremor, which has been recognized dominantly in subduction zones, and aseismic slip or creep. So now over here we're at sort of plate tectonic deformation rates. And the information that she has, that she synthesized on this diagram, this is coming from geophysical observations dominantly. My research program focuses on the rock record of these phenomena by studying exhumed faults. And so this photograph here is a view that many of you've seen if you've come up to Logan, Utah, of the exhumed Wasatch fault zone. Exhumed faults are where deformation occurs at depth in the earth in the past. And the reason that I study these exhumed faults is because they provide a window into deformation mechanisms, the in situ mechanics of earthquake processes, how heat and perhaps fluids, and therefore heat, are transferred through the crust and even through the lithosphere. And importantly, the rheological changes or the earth material property changes that are associated with these phenomena. And the way that my research group and I study this is by looking at, well, one way is by looking at hematite fault surfaces. So this is a simplified geologic map, just pointing out some of the locations of fault rocks and fault systems that we're actively working on right now from the North American Cordillera. And on the right, this is a series of field photographs showing you what some of these hematite-coated fault surfaces look like in these locations. You can see these two examples right here, C and G. These are what we call hematite fault mirrors. We're going to look at these more today. These are high gloss, light reflective surfaces. Sometimes you can see your face in them, and they comprise nanoparticles. The contrast to that is these surfaces here, they're a little bit metallic, they're striated, undulatory. This surface in the eastern Denali fault zone and this surface from the southernmost San Andreas fault in Mecca Hills, these kinds of appearances of hematite-coated fault surfaces is quite common. Okay, so this, I would say, the vast majority of hematite-coated fault surfaces that I work on tend to look like this, or that I observe in the field. Another place we've been working is the Hurricane Fault. This particular photograph comes from that spectacular exposure along Highway 9 as you're going up towards Zion. Okay, so this is a bedrock fault scarp, and it's also a mirror. It's actually a silica mirror. There are little hematite lenses on it. And the reason why I am drawn to iron oxides is because, and I'm going to suggest this to you today in this talk, their textures tell us something about how these materials are deforming. And the uranium, thorium, helium data patterns that we get from these rocks, because they're amenable to uranium, thorium, helium dating, they can tell us something about the temperatures, the timing, and the processes of deformation. So the talk today is really going to be in three parts. The first part of the talk, I'm going to walk you through a case study that is purely based on nanotextural and nanochemical observations from a hematite fault mirror that have allowed us to track temperature-induced transformations during an earthquake. In the second part of the talk, I'm going to discuss how we can interpret hematite uranium, thorium, helium thermochronometry dates from fault rocks. And part of that is predicated on us understanding something about the textures and the grain sizes that we observe. Finally, I'm going to combine these two approaches and talk about data that we have from the Wasatch Footwall Damage Zone in the southern Brigham City segment. Okay, so this is a diagram that has two y-axes, and on the left, what I'm showing you here is, I'm showing you here temperature and slip velocity on the y-axis as a function of time, and this parameter here on the right y-axis is shear stress. So the curves that I'm showing you here, this is sort of a schematic of an earthquake. And what we see in this diagram is that as time As time progresses, the shear stress builds up, builds up, builds up, builds up. Eventually, you reach that yield strength of the rock. It fails, and the strength of the rock dramatically drops. As that's happening, slip velocity dramatically increases, and temperature follows right behind. So this is this red curve right here. After the earthquake rupture has passed, you see the decay in the temperature signature. And that decay is intimately associated with a re-strengthening of the rock materials. So we see this dramatic weakening and then re-strengthening of the materials during an earthquake. But an important takeaway from this graph is that most of the energy during an earthquake dissipates in the form of heat. It's about 85 to 90% doing an energy budget calculation, and the rest of the energy is given off to wear or seismic radiation. And this is important because we can then look for signatures of these temperature pulses in the rock record. And so this is a sample of a hematite fault mirror from El Laco, Chile, which is an iron ore deposit. So you can see this high gloss, light reflective surface. At the margins, there are some slicken lines. And this is what this surface looks like in cross section. It is quite planar. And what you'll see in the next series of slides is that the textures that we observe away from the fault are different than the textures that we observe right at the slip interface. So this is a color image of a scanning electron microscope, secondary electron image, showing that away from the fault, the sample comprises sort of intergrown hematite plates with quartz. Okay, so I want you to remember this image. This is what the material looks like away from the fault. At the slip surface, the textures that we see are quite different. They look like this. So the slip surface is just outside of the field of view here. And now, let's go back. So note the scale bar here. We're at 50 microns, right? Now the scale is, here's 2 microns. Okay. So not only has the grain size been reduced, but the textures that we see are markedly different. This entire fault surface over the scale of centimeters across it is characterized by these polygonal crystals that are interlocking and that in secondary electron images appear to have no pore space between them. In plan view, this is what the fault surface looks like. So this is actually an SEM image that was taken on an Apreo field emission SEM that was on demo here at the U, and Brian called me and was like, oh my gosh, you gotta come try this out. And I was like, oh, I've got a sample. So I came down, and this is the images that we acquired from that Apreo. And I want to come back to the textures here in a moment. But we can dig a little bit more using some additional technology. So one of the things that we did was acquire electron backscattered diffraction data on this fault surface. And it was Fenan Shen, our lab manager, who helped me acquire this data. And when I gave this sample to Fenan, I said, so Fenan, I'd like to get EBSD data on this surface because I want to know, first of all, is this stuff crystalline, and indeed, is it hematite, and what its crystallographic preferred orientation is. So some of you may be familiar with this tool, EBSD. This is a mechanism by which you can get the modal mineralogy, you can get the orientation of crystals in your sample. And so I gave her this specimen, and she said, how do you want me to prepare it? How should I polish it? And I said, well, I don't want you to do that. And she was like, I don't think it's going to work. And those of you who have done EBSD know that there's a very rigorous polishing routine that's required. And so I said, well, let's just try. And it actually worked. And so we were able to index the fault surface. And what you can see is that the surface comprises these hematite nanoparticles. Okay? And I don't have in this particular talk the pole figure diagram, but hopefully you can take my word for it that there is no crystallographic preferred orientation to these hematite grains. okay? So what we learned from this analysis, is that, first of all, this material is in fact hematite. These polygonal grains are hematite. We learned that there was no crystallographic preferred orientation, and we learned something else really cool. She did high resolution scans, rescanning an area of the fault surface in which magnetite was indexed. Okay, we thought, oh, is that an artifact? Is that not real? And indeed, there are magnetite nanoparticles around some of the polygonal grain boundaries. Okay, you might say, well, why is that significant? Jim Evans had suggested that during an earthquake on some of these fault mirrors, that there was high temperature iron reduction. Okay, and so that you actually produced reduced iron on the Wasatch fault mirrors, and so we were seeing it here on this Chile fault surface as well. We wanted to delve in a little bit further, and so we used the transmission electron microscope here at the U, first having to use focused ion beam milling to make a fib lamellae. Working, this is Ian Harvey here and 2 students from our Native American Student Mentoring Program, working with Brian on the TEM, we learned that the polygonal grains had at their interstices silica. So what you're looking at here is an EDS map of the fib lamellae, and each of these pink spots is silica. So silica is occurring along grain boundaries. It's also occurring in spherical inclusions within the hematite. And it turns out that some of this silica is actually amorphous. So the combination of the spherical droplets of silica completely encased within these polygonal grains and the presence of amorphous silica throughout the upper few microns of the fault surface suggests to us, again, that there may have been on this slip surface during some kind of deformation event. We took it a step further and acquired fields data, electron energy loss spectroscopy data on this sample at the Gatan factory. I believe that's in Berkeley, right? Is that right? California. Close. Close, close. Okay, so we acquired EELS data, and what we could see is now we're down to the scale 50, nope. Now we're down to the scale 50 nanometers right here. Okay, and so here are these thin films of silica that are encasing those polygonal grains, and this right here, this region, one of these spherical silica droplets within the grain. So this was another piece of evidence that now in this deformed portion of the sample, there has been this network of silica films, again, that are encasing our polygonal hematite grains. And so we can combine all of this together into sort of a series of cartoons of what we think is happening. So there was, we would suggest, an earthquake that was accommodated on this slip surface, and there was significant grain size reduction. The material that is within this deformed domain right at the fault surface is markedly finer grained compared to the material away from the fault. And the friction generated heat throughout this deforming layer causes the material effectively to melt. And what we then see is we see this mixing, although it's immiscible, this mixing between hematite and silica that results in these, again, spherical droplets of silica within the hematite. And so the question is, okay, this rock, it got hot and weak. What happens next? So I want to return to this image of the fault surface right here. And so when I look at this image, well, I should ask you guys, how many networks of polygonal grains do you see here? 1,000. Oh. So I guess what I should say is, What do you do you notice that there are black lines and white lines?
Yes.
Okay. So I'll be honest, it took us a while to figure out what the hell those white lines are. Okay. The black lines, it was straightforward to us that these are recessed regions that are grain boundaries, right? Right. The white lines, is there something chemically different about this? So this is a secondary electron image. Sometimes there can be a little bit of chemical information in there, but it shouldn't be. It should be topography. And it turns out from doing some very long count, high spatial analysis on this sample, there is no chemical difference from these white lines to the black lines. These regions, these are ridges. Okay. These are ridges. Here. So what this is, as this material is quenching, this is fault material that's puckering up into hematite that had recrystallized on the other side of the fault. You might say, well, how do you know it's hematite? Well, we are working in iron ore. But maybe there's some other rock type there. It's just interesting to me that when you do a grain size distribution of the polygonal grains, so what do I mean by that? You measure the diameter. I think we measured like 300 diameters of these polygonal grains, and then you measure the diameter of the white lines. They're exactly the same. So it's likely that whatever was on the other side of the fault was iron oxide as well. And so this fault surface is localized within those polygonal grains. And it turns out that the growth of nanoparticles actually makes material stronger than if the grain size had been larger. In addition, I'm just going to step back because this is actually interesting. I learned that the presence of lamellar twins, do you guys see this right here? These twins, these rectangular lines, and they exist not only in the black lines, but also where's a white? Right here. So that's another indication the material is probably hematite. Hematite can form these 85-degree misorientations. Lamellar twins in materials science literature are used to strengthen the rock. And the fact that you have this ridge network forming, these are collectively pieces of evidence that suggest that this fault rock is strengthening as the temperature is decreasing. Okay? So what's interesting about this is the weakening, the creation of effectively this melt layer that then quenches, preconditions this fault surface to re-strengthen. And this is significant, although I will admit this particular fault was something that was given to me by a now deceased emeritus professor, Spencer Tetley at the University of Arizona. So I don't have the field context, but if you place this into a fault damage zone, why this might be significant is because the re-strengthening of the rock means that the next time that there's a deformation event, it might shift to a different fault surface. The analogy to this would be pseudotacholites. People think that when a pseudotacholite forms, it welds the fault rock, and that might cause where strain is accommodated to shift in a fault zone. Okay, so switching gears to the second part of the talk, I am actually a low temperature thermochronologist. And thermochronology, as many of you are aware, embedded in this word, is temperature and time. Traditionally, thermochronology and low temperature thermochronology is used to quantify the movement of rocks through the subsurface of the Earth. Okay, so you want to know when were the Wasatch Mountains exhumed. You acquire apatite, uranium, helium data from the host rock. Okay, so what I'm showing you here, this is the first of several Caltech plots. And some of you have heard me say this. I've been taught these are plots of something versus nothing. I don't know, but these are something. These are something. So there is kind of a x-axis. Okay, so this is closure temperature as a function of thermochronometry system. And traditionally, low temperature thermochronology, again, is used to quantify tectonic processes on the scale, John mentioned, we're talking hundreds of meters to hundreds of kilometers, right? And over perhaps million-year timescales. What I'm showing you here is the hematite uranium, thorium, helium closure temperature. And that ranges from 25 degrees Celsius to 250 degrees Celsius and even higher. We're going to talk about what's controlling that variation. So hematite is amenable to uranium, thorium, helium dating because it incorporates trace amounts of isotopes of uranium and thorium into its crystal structure. Okay? It does not have initial helium, so negligible initial helium, and that helium is retained over geologic timescales. And so that helium decays to isotopes of lead, and it produces alpha particles. Okay? So the fundamentals of the uranium, thorium, helium system is that we can measure our parent, the amount of parent that we have in our aliquot of interest. We can measure the amount of helium, and we are ultimately solving for time. Okay? But in this talk, this time, like what does this time mean, is going to be, very important. So in order to begin to interpret hematite helium dates from fault rocks, or just hematite helium dates from, say, hematite in a vein, understanding what this time means, the first step is actually returning to what we've learned from micro and nano textures. So one of the first things that we do is nano to micro textural analysis using a scanning electron microscope. What I'm showing you here are a number of images of what hematite looks like. Note the scale bar. This one's kind of zoomed out because it's this megacrystic specularite, but 100 microns, and you can see some of these scale bars. Here we are now at 100 microns. These are all examples from fault rocks. Okay? So part of the reason that we do this is because to first order the textures and the grain morphologies that we see, these are telling us about fault zone process. Even if you're not sure about the fault zone process, surely we can agree that whatever happened here is different than what happened here. These are high aspect ratio foliated plates. And if I didn't have an EDS map of that, I would say, oh, is that clay? Right? Because it looks like a clay fabric. So the textures that we're observing tell us something about fault zone process. But the other reason why we look at these rocks at this scale as part of our workflow is because we need to characterize the closure temperature of our system. Okay? So we need to know something about the grain size distributions. So closure temperature, just pause here. Closure temperature is the temperature at which helium is quantitatively retained in our crystal of interest. So you might be familiar with the apatite helium system or the zircon helium system. You could have closure temperatures for the uranium lead system, argon. That's a temperature that daughter product's going to be retained. And in the hematite system, okay, what is controlling this is the grain size. And I'm going to show you that here in more detail. So we know from diffusion experiments, from 4-3 diffusion experiments, and now we have some insight from density functional theory, that the closure temperature in hematite varies as a function of grain size, but there's this added complexity. Most hematite that we analyze is not just a single crystal, but it's actually a polycrystalline aliquot. Because I'm pretty good, although right now I feel a little bit out of practice, but I'm pretty good with number 5 tweezers. But I am not that good that I can extract one of these grains. Okay, I wish. The future of thermochron. The limitation there is there enough uranium and thorium to measure in that tiny 1 micron diameter particle? Okay, that's another issue. But when we are analyzing material, we are commonly analyzing polycrystalline aliquots. So what this means is that any one of the aliquots that we analyze, depending on its grain size distribution, could have a range of closure temperatures. All right? So what you're looking at here, this is closure temperature as a function of equivalent spherical radius, or you could think diffusion domain length scale. And I've kept it simple because these are just for this grain size or this grain size or this grain size. But let's say you had all 3 grain sizes in your sample. It becomes complicated, right? And your date kind of represents this mixed date. So one of the things that we do as part of our analysis is we do grain size distribution characterization using image J and our SEM images, and then using our best understanding of diffusion kinetics, worked by Ken Farley dominantly and Pete Reiners and Nate Evanson, we use the diffusion kinetics to then calculate a closure temperature. So here in these 2 examples, you're seeing the grain size distributions and then the calculated closure temperatures in blue associated with that, okay? And so you have to do this because otherwise you don't know where on this plot you are, okay? This is important because unlike apatite and zircon, well, I should say, no, unlike apatite and zircon, hematite can form at temperatures greater than or lower than its closure temperature. It's a secondary phase. Also, because of the low temperature sensitivity and because we're working in fault rocks, there's a high chance of open system behavior. You could have ongoing deformation that changes your grain size distribution, cataclasis. You could have fluids moving through the system, friction-generated heat. So the dates that you acquire reflect the conditions of formation and the post-formation thermal history. So when I was last here, I mean, we did not realize, I mean, we kind of knew, but we did not realize this. And so the workflow that we have developed, that is what's been going on for the last, like, 7 years. Okay, so how can we interpret these data? So this comes back to, Casey, we were talking about this earlier, these kind of data interpretations for your hematite. This is, okay. So this is a thought experiment. Let's say that your sample has a closure temperature that would be 120 degrees C. So its grain size distribution equates to 120 degrees C closure temperature. If your sample forms at temperatures lower than that, remains there throughout its entire history, and you go and sample it, it has all of its helium budget, your date reflects the time at which it crystallized. If that is on a fault surface, it might be synkinematic, and your textures could help you with that. However, if your sample formed at temperatures higher than its closure temperature and later passes through its closure temperature at some later time, it's going to record a cooling age. In this scenario, you're no different than the apatite or zircon in the footwall of a footwall damage zone. Now, again, fault surfaces can host a variety of thermal processes, and so long as those processes happen at temperatures lower than the aliquot's closure temperature, you can record that. So a third possible interpretation is some kind of thermal resetting or non-monotonic cooling history. So now I want to switch gears and in the third and final part of the talk, get to data from the Wasatch Fault Zone. So, open topography. Yes, yes. Yes. So you all are, of course, very familiar with this part of the world. And we have specifically been working, I feel like I had to like put this down or it's going to drive me crazy. But we have been working in the southern Brigham City segment of the Wasatch Fault Zone, okay? And this is a place where the Farmington Canyon complex has been exhumed. Now we're at the mouth of Pearson's Canyon, looking up and across through the damage zone. And it's this damage zone that is characterized by, I think I said to someone earlier, I mean, there's just tens of thousands of small faults, but importantly, hematite-coated faults in this damage zone, okay? So the work that I'm going to show you now, this is work of Dermott and his undergrad research assistant, Kelsey Wetzel. So, yes, I know. So these are examples of hematite-coated fault surfaces in the Wasatch Fault Zone. These are fault mirrors. And they occur in the field. They're planar, they're arcuate, they're exposed at sort of the centimeter at most, maybe 3/4 of a meter scale, all faults. And when we look for offset we have seen is about 10 centimeters. Small displacement. In places they show an iridescence, and this is something that Jim Evans, in the original paper about these in 2014, he still is, I think, quite obsessed with this iridescence and what it's doing there. Okay. Interestingly, what we know now is that many of these mirrors started off their life as specularite veins. Okay, and so here on the left, you're looking at one of these specularite veins in the Farmington Canyon complex, and on the right is an example of a fault mirror, and you can see that specularite right here just sort of peeking through. And this is important because I think that these veins serve as, rheologically weak zones in a much stronger granite, and so that is where strain is being localized following the hematite vein formation. So you can imagine with this sort of vein to mirror transition that we see a variety of textures at the nanoscale. Okay? But one of the things that I discovered that I did not expect to see there was the presence of these polygonal grains. So this work actually predates the work that I showed you at the beginning of the talk that was just published this year. But with field emission CM, we recognize for the first time that in places along this fault surface, that there are these equant polygonal grains that have this sort of annealed or sintered texture to them. And when I first saw this, it reminded me of regime 3 quartz. So that is a high temperature deformation mechanism that I studied when I was a master's student working with Jane. And so I was like, oh my gosh, this sort of equant triple junction forming grains, this looks like that. I wonder if this is an indication of heat. So what kinds of processes might be responsible for heat generation on this surface? Well, what I'm talking about here is either shear heating or asperity flash heating. So asperity flash heating is a process where at frictional contacts, so at surface roughness points, there is really high normal stress, really high contact stress, and the rate of heat generation dramatically outpaces heat dissipation. So the temperatures, you can, well, with parameters, you can get any temperature you want, but the temperatures that you can get on these surfaces exceed 1,000 degrees C. Okay. So this is important because, as I mentioned before, heat makes rocks weak. This reduces the coefficient of friction, or mu, and this is what allows an earthquake to propagate. And this is important for the uranium, thorium, helium system because this heat can induce helium loss. Or I should say this is a hypothesis that we have, right? These are high temperature, short duration thermal pulses. So how are you going to get helium loss? Well, you're going to get helium loss by thermally activated volume diffusion. But if you recrystallize the grains, that would also liberate helium as well. So over the years, we have acquired a lot of hematite, uranium, thorium, helium data from the Wasatch Fault. So this is another one of these Caltech plots. This is hematite, uranium, thorium, helium date in millions of years. And each of these data points is an individual analysis with its 2 sigma analytical uncertainties, and it's classified by sample. The triangles are specularite vein samples, and the circles are from data that we have extracted directly from the fault mirror interface. What's going on with these triangles is a separate talk, but for those of you that are familiar with regional tectonics, you'll recognize data that is consistent with the timing of the severe orogeny. But we also see dates that are shading older than that. So there's the possibility that the original precipitation events that we're seeing here are much older than the severe, and this is the subject of ongoing work. So one of the first things that we can observe here is the hematite fault mirror dates, the circles, are less than the fault vein dates. And in a few cases, Rob has data where he has, so this is, let's see, here's an example. This one right here, these triangles. So this is a vein, and then here's the matching fault surface. So to first order, there has been helium loss from the fault surfaces, but the question is why? Okay, and the reason why this why matters is we are in the footwall of a fault. Could this just be simple footwall exhumation? So now what you're looking at is the data as sort of a PDF, like how you might display zircon, detrital zircon data. And so these are all of the individual hematite helium dates and their relative probability. And what I'm showing you now is the apatite helium date for the host rock. So we have apatite helium data that is providing constraints on the timing of that footwall exhumation in the southern Brigham City segment. And the average of those dates is about 4.5 million years. So the hematite helium closure temperature for these aliquots that we analyzed from our SM work is 95 to 115 degrees C. So 50% of our hematite helium dates are younger than the apatite helium date, and yet they have a higher closure temperature. So these dates cannot simply reflect just ambient cooling of the footwall, okay? If that was the case, all of this data should plot over here, okay? So the other thing that we did was Rob took a subset of aliquots, and before he analyzed them, he pre-screened them with the scanning electron microscope to look at their textures. So remember I said these things started off their lives as veins. They have strain localization and ultimately progressive deformation, grain size reduction. There's cataclastic textures. There are these polygonal grains. And I said to Rob, I said, I want you to try to target within each sample the range of textures that you see. And we are going to date them, okay? So those are these aliquots in the upper right. So the aliquots were pre-screened with the SEM to purposefully select the range of temperatures. So here we're zooming in on this y-axis from 7 MA all the way to present day. Here is our apatite helium benchmark, 4.5 million years. And not all, but most of the samples that are characterized by textures that look like this, okay? These polygonal grains that we think suggest a high temperature process, they yield dates that are younger than the apatite helium date. Some of them, of course, are older. And if you think that this relation, these textures, reflects a high temperature event, perhaps friction generated heat during an earthquake, the fact that some of these aliquots contain these textures says when they were active and perhaps accommodated earthquake slip was at a time period prior to passing through the apatite helium closure temperature, okay? So one of the questions we had was, how hot are these surfaces getting? So what you're looking at here are the results of a calculation that Rob did, where he is calculating the asperity flash heating temperature and the thermal history of one of these surfaces using the formulation of Jim Rice and the relevant material properties for our hematite fault mirrors. And for an asperity that is 20 microns, you can generate a peak temperature of 1200 plus degrees Celsius in this material at one of these localized asperities. And so the question we had is that temperature for this amount of time sufficient to induce helium loss from our material that's right at the fault surface? And that's what you're seeing over here on the right. This is a plot of helium loss as a function of distance. And this is the region that we are sampling within 200 microns of the fault surface. And for the relevant grain sizes that we see, the aliquots are experiencing upwards of 80% helium loss. So the flash heating is sufficient to induce hematite helium loss in our analyzed aliquots. Now, it's complicated, right? It always is. A question that I get is, okay, so is each one of those dates that you have there an individual earthquake? No. No. Because any given fault surface, and indeed any given aliquot that we extract from one of these fault surfaces, has a complex distribution of asperities on it, and therefore heat generated during one of those slip events. That's a complex heat distribution in X and Y and in Z, okay? So an aliquot that we analyze is going to be an integrated signal of helium loss. Now, I had a lot of slides already, so I didn't put this in. You know, we have indications that some of these slip surfaces have multiple slicken line orientations on them. Jim has one sample where he says that he thinks he sees 7 different slicken line orientations on it for CM work. Okay, that was in his 2014 paper. So these fault surfaces are repeatedly reactivated, okay, in this footwall damage zone. But, you know, that's the complexity, but if you try to see, you know, every cloud has a silver lining, thermochronometry, like what we're doing here is we're actually using it as a fault slip thermometer. So in the same way that people who work on pseudotacholites say, this is evidence of earthquake in a rock record, if you see evidence both texturally combined with your thermochronometry data patterns of flash heating, you are using these tools as a thermometer, and you can model that, okay? We wanted to just make sure, I mean, maybe, right? You guys are thinking, maybe. So my postdoc, Gabriele, when he was here as part of my NSF career grant, he worked in Greg Hurth's lab at Brown University. And Greg is an expert in rock mechanics. And he performed rotary shear experiments where he deformed a specular hematite boulder from the Wellsville Mountains, okay, in a rotary shear apparatus. So he slid a silica carbide ring, okay, on a plate of hematite. And what you're looking at here is what one of those experimentally generated fault surfaces looks like. It's characterized by gouge, and then there are fault mirrors. So what he did was he characterized the fault surface prior to deformation in a couple of different ways. This material was megacrystic spectrum. So he was actually able to isolate individual plates from the polycrystalline aliquot, and that's what these orange symbols are here. And you can see, well, wait a minute, the dates vary by about 100 million years. And you know, we got that data, and on the one hand, we were like, well, that's not particularly reproducible as a benchmark, but we saw that there was a positive relationship with grain size. Okay, so there's no, of course, no x-axis here, but in this paper that's coming out, there is a plot of date versus grain size, and there is a positive relationship. So that date variation is being controlled by grain size and thus closure temperature. So what he did was, in ethanol, he lightly mortared and pestled starting material, undeformed material, and then he analyzed that. So that's what these black symbols are right here. This is the undeformed starting material and the range of undeformed dates. Here are the results of the gouge. So this material right here, it overlaps within 2 sigma of the undeformed starting material from the slab. And then here are aliquots that he extracted from the fault mirror. Okay, we have one flyer here that experienced uranium volatilization during analysis. But you can actually do a calculation based on these dates, what the percent helium loss is, comparing the deformed aliquots with the other. And in these fault mirror zones, we observe up to 70% helium loss. Okay, so this is significant because that is happening during deformation. And it's not happening everywhere. It's happening where these mirrors exist. And we suggest in this paper that this is the product of asperity flash heating. So what does that mean for our natural fault rocks? Well, I think it means we're not crazy, so that's good. I'm cognizant of the time, and in the remaining couple of minutes, I just want to show you something else about the Wasatch Fault Zone. So I've mentioned these hematite-coated fault surfaces and that they're everywhere in the damage zone. They're not the only fault mirror that we observe, and this is the work of my former master student, Leah Hauser. So there are these silica-rich slip surfaces that cut across the Farmington Canyon complex as well. They are also thin slip surfaces, they're reflective, high gloss, and they comprise nanoparticles. So we see these same polygonal grains right at the slip surface. And the other thing that we observe is crystals, and these are actually crystals, and that's important, you'll see here in a second, growing. So one of the things that might reflect is if this material had been amorphous, when silica goes from amorphous to crystalline, there's a volume change. And so you would end up with these void spaces. And indeed, when you look down on the fault surface in the SEM, you see all these pore spaces. The other thing it turns out, and this is where Brian has been hugely helpful, is that these textures, these polygonal grains, it's tempting to think that they're fully crystalline, but they're not. They're characterized by amorphous particles, or they're characterized by an amorphous interior, and in other TEM images that we see, they're actually studded by little crystallites. So it's as if we are capturing incipient crystallization of this material. The other interesting thing about this is that, so this is TEM work, so you're looking at a fib lamellae of one of these silica-rich fault surfaces, and this is a nitrogen EDS map, a STEM EDS map. It turns out that in addition to a bunch of silica and all these nanoparticles, there is polycrystalline anatase, or titanium dioxide, that has nitrogen substituted in it. We thought, well, that was unexpected, and what does that mean? And Leah started looking into the materials science literature and into the photocatalytic literature, and it turns out that companies dope their solar cells, which are sometimes made of titanium dioxide, with nitrogen to increase their photocatalytic capabilities. They do that in high temperature environments. So they force nitrogen into the anatase in high temperature environments. Now, I think it's sort of an outstanding question, like where is this nitrogen coming from? But this is a possible suggestion of high temperatures on these slip surfaces as well. So it's not just the hematite-coated fault surfaces, but it's also these silica-coated fault surfaces that have experienced high temperatures, we think, due to small earthquakes that are accommodated on them. And so what I would suggest to you is that what we are capturing are earthquakes that are happening. These are nano to micro earthquakes based on the offsets and the size of the slip patches. They're happening less than 4.5 million years in the footwall damage zone, okay? Does this mean that these surfaces were not active prior to that? As I explained before, no. They are repeatedly reactivated. It's just our ability to see that with low temperature thermochron. It requires us being at temperatures lower than the closure temperature of our systems. And so the last thing that I'll just leave you with is that, you know, I think to first order, when we step back and think about these hematite-coated fault surfaces, we're actually seeing the potential for this material of deformation processes. So what you're looking at here is a plot of minimum peak temperature. And so this would be temperature occurring on a fault surface. And each one of these different bars represents a geochemical tool that has been developed, such as the maturation of organic biomarkers. Okay, this is the work of Praktika Polisar and Heather Savage, for example. So these are tools that help us take the temperature of faults. So I would suggest to you that hematite helium thermal resetting is another tool that we can use to take the temperature of fault, and that in some cases, the textures and the data patterns are telling us about processes that are related to earthquakes. But in other cases, the textures can look quite different. And perhaps we can start to learn things about what's happening at the lower end of the slip rate spectrum from these rocks as well. And so with that, I will take any questions that you guys have.